No matter what. Hi, welcome to Earth and Space Science. This is October 2nd, so this is the day that you guys will have a sub, right? And so this is my first time. I'm using this program called Screencastify that is recording my screen. Hopefully this goes well. I'm new to this, so if there are any weird technical difficulties, I'm sorry. But we'll work through it together, okay? Today in class we're going to be learning about astronomy. We're in this astronomy unit. We're going to keep going with this this theme. Our first slide here, the word astronomy is in orange, and I want to point out and I want to remind you right now, if the text is in orange, you're going to be on the hook for that. You'll be expected to know that. Okay, so we're going to be taking a little bit of notes. I've got 4 slides today that you'll be covering. Excuse me, and so you will need to take some notes today. So go grab your notebook, get ready to go, and we'll get started. Again, remember, orange text is stuff that you will be responsible for knowing. There are 2 things today that we're going to be covering that I guarantee will be on your test. Okay, anything that's in orange, I may end up throwing on the test or in a quiz of some sort, but I guarantee you 2 things that we'll talk about today, and I will point those out when we get to them, you will be asked about on a test. Okay, so just keep that in mind as we go through here. All right. So last class we were learning about astronomy, and we talked about this early ancient astronomy where the Greeks thought that we lived inside of a sphere. Right, and I use this as an example. We lived inside of this sphere, and the Earth was at the center of everything. So this light bulb that's in here, imagine that that's the Earth, inside of everything. And then the stars were fixed on the outside of the sphere, or the inside of the sphere, and it rotated around us, and the Earth was the center of all of it. Okay, this is what the Greeks believed. And so the sun and the moon and everything, well, the stars were mounted there, but there were some other things that didn't quite make sense, like the sun, the moon, and the 5 planets, the planetae, the wanderers, okay? Mercury, Venus, Mars, Jupiter, Saturn. Remember, you couldn't see the other planets because you don't have a telescope at that point. We kind of stopped there with the history last time, and we got into big numbers. We watched this video by Neil deGrasse Tyson about numbers, and then we started the Big Bang, and we did this concept map, or bubble web, whatever you want to call it. So we are, during this lesson, during this unit, in the past I've taught a separate lesson on astronomy history, and then a separate lesson on the Big Bang theory, and a separate lesson on stellar evolution, star evolution, and how stars change throughout their life cycle, and then lots of different smaller sections. This time, what I'm trying to do this year is put it all together in one, and I'll admit that at the beginning, the astronomy history doesn't quite line up with what we're talking about as far as major overarching concepts. So while the Greek thing doesn't quite line up with the Big Bang, I promise that as we get into the unit, when we talk about Copernicus and Galileo and Kepler and Hawking and all these other people, things will start to line up. So if they don't line up now, that's okay. Just understand that we're kind of merging 2 ideas together that are related, but we're merging them together into one. So I've shown you this slide. I showed you this last time. We talked a little bit about how this is a timeline. You can always refer back to this if you need to. But this is where we're going to start. The Ptolemaic system. We're back in the astronomy history portion of this. The Ptolemaic system. Now, Ptolemy was a Greek. I'm not sure if this is the day that he lived, or that he's born, or the day that he died, or if this was when he first published his ideas out for the world to see. But regardless, you can see he was a Greek, and he lived in about, you can see kind of about when he lived, 141, thereabouts, okay? Now, the Greeks had already, for hundreds of years, accepted this model of Earth being in the center of the universe and everything going around us, from east to west, and it just rotated around us, okay? And it makes sense for the stars. And remember, the Greeks came up with that whole mythology based on the moon and the sun and the planets, the 5 planets. Jupiter was their main god. For the Romans, Jupiter became Zeus, and Mars became Ares, the god of war, and Venus became Aphrodite, and I'm not sure what Saturn. I'm not sure the mythology of Saturn, but Mercury became Hermes. Okay, and they're based loosely on reality because Mercury, the only time that you can actually see Mercury in the night sky is right before the sun rises. That's the only time you get to see it. In fact, I've never actually seen Mercury. That's one planet that I haven't seen. I've seen Venus, Mars, Jupiter, Saturn, Neptune, Uranus. I've never seen Pluto, and I've never seen Mercury. But Mercury comes up right before the sun. And if you think back to Greek mythology, if you know anything about Greek mythology, Mercury, the god, rode a chariot across the sky, like ushering in the sun. Right? So it's loosely based in reality and science. But it was a big deal. Well, nobody could really explain the motions of the planets in the night sky. The sun and the moon, sure. If we were the center, they would go around us, no big deal. But the planets, they took a very weird path that they couldn't explain. And so this guy Ptolemy came up with a system that explained it. He used circular orbits, the Earth in the center, and the planets going around us, just like everything else. But there's this time when planets go in what we call retrograde. And retrograde is where it's an apparent backwards motion in the night sky. And I have a video. I don't know how to show it to you on this, so I'll show it to you. Actually, you know what I'll do? I'll just have you pause it here in just a minute, and I'll tell you when to pause and go watch the video that I'll upload on Schoology. That's how I'll do it. But the retrograde motion is the apparent backwards motion of a planet in the night sky. And it's caused when an inner planet laps an outer planet. Now, all the planets are moving around the sun in the same direction at roughly the same speed. But if you've ever run on a track, or at least seen the track out by the football field, or you've ever played a racing game, video game, you'll know that the inside lane is shorter. The inside lane is shorter than the outside lane. And so it's the same way in the solar system. The inside planets have a shorter path. Therefore, their year is longer. Their orbital period is longer. Mercury's orbital period is 88 Earth days. Earth's orbital period is 365 and a quarter days. Pluto, if I remember right, I'm trying to think back, I think it's like 1,026 days or something. You can fact check me there and tell me if I'm wrong. So they're moving around at roughly the same speed, but the path is shorter, so they have shorter distances to go. And whenever an inside planet laps an outside planet, from the inside planet's perspective, you get this retrograde motion, where it appears to move backwards in the night sky. All right? And that's a real phenomenon, a real optical illusion that we see from here. Imagine that you're driving down, somebody else is driving the car, you're driving down the highway and you put like your blinders on up against the window and you're staring out. And the car that you're in passes another car. Pass it. Okay? It's going this way and you're going this way and you're both going in the same direction, but you go faster and you pass it. Well, what you would see, if you're doing this out the window, what you would see is the back end of the car, and then the middle of the car, and then the front of the car as it moves backwards. It appears to be moving backwards, but it's not, and we know it's not. You're just moving at different speeds. That's retrograde motion. Okay? That's what it is. So pause now and go back to Schoology and go watch the video that I posted there. It's BBC. It's a guy that's struggling to draw with a stick. It's really funny, kind of. And he explains it pretty well. So go watch that. And if you still have more questions, there's lots of videos out there on retrograde motion. Okay? Well, Ptolemy was the first person to be able to use the geocentric model and use or explain retrograde. And he did it by using these things called epicycles. Now, epicycles are where he thought that the planets actually did a little curlicue, like a spirograph, if you've ever played with a spirograph as a kid, where you put the gear inside of another gear and you put your pin on there and you draw cool shapes. That's sort of like what he thought the orbit was like of other planets. And he ended up being wrong. But it was pretty good. It's a pretty good explanation for the information that they had at the time. Okay? We're going to stop going on with the history of astronomy, and we're going to jump into the Big Bang. And I've got to move fast because my video ends in 5 minutes. So I'm moving fast, okay? Time begins. Remember, everything that's in orange you're responsible for. We're at the beginning of the Big Bang. Time begins here, 13.7 billion years ago. Now, if you think back to when, if you're having a hard time remembering this, remember the song. Our whole universe was in a hot, dense state, and nearly 14 billion years ago, expansion started. Wait, right. 14 billion years ago is what they round up to. 13.7 billion years is the number that you need to know for this class. 13.7 is the number you need to know for this class, but it might help you if you remember 14 billion years ago, because then you can round down or whatever. You can figure it out from there. Okay? Time began at 13.7 billion years ago. The universe began at 13.7 billion years ago. What does that mean? Like, what was there before? Remember, there's all those questions we'll never be able to answer. And we won't be able to answer what was there before, or why, or what's outside of the universe. Those are things that we can't know. But the universe started off as a singularity. At 13.7 years ago, it expanded rapidly. It started off, we think of this, and even this image here that I've given you, we think of it as being like a bomb. Big explosion, or a grenade or something going off. And this image here, that's kind of what it depicts, but it wasn't really like that at all. Instead, it was more like a balloon. Taking a balloon that doesn't exist and blowing it up. But it was very violent. You don't really think of balloons being inflated as violent, but it was violent. Lots and lots and lots of energy. In fact, it was all the energy that is in the world today. Very violent. Rapid expansion. Not explosion, but expansion. Okay? And in that instant of pure energy, the universe was created. And it's expanding today. We'll get into that later. About 3 minutes after the Big Bang, the universe was nothing but pure energy, and it was extremely hot. Much too hot to have stuff. Couldn't have things yet. Everything was just energy floating around in the universe. And about the 3-minute mark, things started cooling off. And it started cooling off because it was moving around and spreading out. Right? It was diffusing into the new space that was being created as it expanded. And as it's expanding, as the energy is spreading out, it starts to slow down and it starts to cool off. And that's important because as it's still extremely hot, but it starts to cool off. And as it cools off, the energy is converted into matter. We know that this can happen because of Albert Einstein. He came up with this famous equation, E equals mc squared. E stands for energy, M stands for matter, C stands for the speed of light. Okay? E equals mc squared. And energy was able to be converted from energy into matter using this equation. Alright? When you take a temperature of something, you take a temperature of, I don't know, chicken or something as you're cooking it. What you're really doing is you're sticking the probe into the chicken and you're measuring the kinetic energy of the particles. That's what measuring temperature really is. Kinetic energy of particles, of atoms. And so, when you're measuring raw chicken, what you're measuring is how fast are those atoms moving. The more energy you give them, the more heat you give them, the faster they move, the more excited they get. Really excited. And as you cool them off, they slow down. Well, you know that as things speed up, or as things heat up, they get bigger. They expand a little bit. So boom, boom, boom. Think about the energy that's there. It's having a hard time as it's bouncing around. It's bouncing in more directions and it's bouncing farther. But as you cool it off, it slows down. Okay? And as it cools off and slows down, it clumps into protons, neutrons, and electrons. Alright. I have less than a minute left on this video. So what I'm going to do is I'm going to stop it here. And I'm going to have you go on to the next video. I didn't plan on there being another one, but there's going to be another one. So you'll have 2 videos to watch. You'll have this one plus the next one. So I'm going to stop this one and then go back to Schoology and open up the next one, and we'll start on this slide.